Welcome everyone to the third lecture video in the Class 11 time series of lecture videos. We'll go ahead and start off here asking how do we go from a bond line structure to a Fisher projection? And so the answer is you've just got to follow the rules for Fisher projections. What are the rules for a Fisher projection? We know that the horizontal substituents are projected up out of the plane of the page, and the vertical substituents are projected back. So if we take this bond line of our RR 3-chloro-2-butanol, what we should do to make it a little easier is go from the staggered conformation to an all-eclipsed conformation where we've got our carbon backbone in the plane of the page. Now if you can visualize yourself in the plane of the page looking to the left, what would you see? You'd see a hydroxyl group to your left, and you'd see a hydrogen to your right on carbon 2. On carbon 3, you would see a chlorine group to the right and a hydrogen to the left. So you can think of a Fisher projection as an all-eclipsed form of a molecule that's the least stable. So Fisher projections are useful, particularly for biologists talking about some molecules that are more difficult to represent in bond line, and being able to compare those molecules with other isomers of the same type, especially for sugars, for example. So it's a type of representation that we should be familiar with by the end of our organic chemistry sequence. So if this operation of going from this bond line to this Fisher projection, or being able to go from this Fisher projection back to the bond line, is unclear, it's something we can practice during our class time. So we'll continue with how we might see test questions written concerning Fisher projections. That's always, something useful. How do I get points and demonstrate my knowledge? Let's put all configurations or stereoisomers of 3-chloro-2-butanol in Fisher projection form. So in A, we have the SR 3-chloro-2-butanol. In B, we have the RS 3-chloro-2-butanol. In C, we've got the RR 3-chloro-2-butanol. And in D, we have the SS 3-chloro-2-butanol. So another thing I would ask students is to be able to look at a Fisher projection and assign the stereocenters as R or S. And this is kind of difficult. I think I alluded to it in the first lecture video for the series, that you might ask me to do an interpretive dance for this, but it's really not too bad once you get the hang of it, to be able to look at this Fisher projection and say to yourself, oh, that's an R stereocenter. We're going clockwise if we put the low priority hydrogen in the back. And similarly, this is an S stereocenter in terms of how we're connecting priorities 1 to 2 to 3 if we put hydrogen in the back. So recall the definition of a diastereomer. It is a stereoisomer not related as an enantiomer. So we still have to remember the definitions for stereoisomer and enantiomer. So stereoisomer is a molecule whose atoms have the same connectivity but a different orientation in space. And an enantiomer is simply a non-superimposable mirror image. So diastereomer is a stereoisomer that's not related as a non-superimposable mirror image. So for biologists, it might be easy to see certain relationships between molecules diagrammed in Fisher projection form versus bond line. Of course, as an organic chemist, my preference is for bond line diagrams. However, sometimes it is easy to see in a Fisher projection whether you have an internal plane of symmetry for a molecule. So how we might phrase questions in an exam concerning Fisher projections, we might, describe each stereoisomer as, stereoisomer A, B, C, or D, and then ask you to give us the relationship between a pair of them. So how are A and C, for example, related? Well, A and C are related not as mirror images, and it's kind of easy to see in this Fisher projection form what is related as a mirror image and what isn't. A and C are definitely not mirror images, they are diastereomers. Similarly, A and D are diastereomers, as are B and C and B and D. However, if you go back up and look, it's kind of easy to see that A and B are enantiomers, that is, they are non-superimposable mirror images, as are C and D. So what am I talking about? I'm talking about the fact that, oh yeah, it kind of looks like, A and B are related as mirror images in terms of, their Fisher projections. Similarly, C and D are related as mirror images. It's almost as though we have a mirror plane between C and D, and so the different groups are reflected in the different areas. Alright, so that pretty much finishes this third lecture video, and we'll continue in the next video with more bond line diagrams and maybe some comment about cis and trans substituted stereoisomers.